Business modeling and simulation. Simulation is the art of statistical abstracted reality. Via a process of abstraction, the modeler is forced to trade off reality, accuracy, and generality. For simplicity, models only include a subset of the variables and interrelationships of the original system. Simulation must be done to an assumed level of detail which permits the objectives to be fully studied without superfluous modelling effort. The model's assumptions, validity, and results must be made transparent to interested parties. Model building forces deep thinking on the true nature of the system being studied. The model is only truly useful if those interested parties who should use the results have formed a group consensus of the true nature and correctness of both the operation of the real system and the simplified simulation model. Simulation systems can include costs. This permits sensitivity analysis of the assumptions applying to a project's revenue potential. This is a far better way of assessing and comparing investments under uncertainty than conventional net present value (NPV) and internal rate of return (IRR). Do people use simulation? Well, vendors will impress you upon their vast business client list. For example, in Auto Simulations Discrete Events July 1986 describes the redesign of a Boots warehouse. In this redesign, they were determining whether crane systems would be more efficient than high-rise, very narrow aisle trucks. Each crane cost over $200,000. Using AutoMod, Boots created a model of the warehouse that incorporated movement, product positioning, demand patterns, pallet and truck capacities, and delivery and replenishment frequencies. Future forecasts were tested at sensitivity analysis. Models were tested using 2, 3, or 4 cranes. Too many cranes were expensive, too few seriously impact customer service. Another interesting company is Swisslog. Swisslog use simulation as an integral part of their business. If you go to Swisslog's website at swisslog.com, you'll see dozens and dozens of case studies of their application of simulation to warehouse design and management. Having built a simulation, they present this to the client, having tested it through sensitivity analysis with different variations of what's called the order profile. Finally, when the client agrees and the simulation is finished, they build the warehouse knowing with certainty that the warehouse design is robust. Verification and validation of simulation models. The validity or significance of a model should be judged by its suitability for a particular purpose. A model is sound and dependable if it accomplishes what is expected of it. This means that validity, as an abstract concept, divorced from purpose, has no useful meaning. What may be an excellent model for one purpose may be misleading and worse than useless for another purpose. J.W. Forrester. The model development process and context. Model development includes problem definition, model building and testing, experimentation, and project implementation and documentation. It's something of a paradox that when a simulation would be at its most useful, it's when it is almost useless. However, it can be very useful in sensitivity analysis of a proposed totally new investment. Unless a model or version of it has been validated for accuracy against an existing system, it should not be used to source absolute system performance figures. The process of model development and validation, correct for the intended use, moves from relative comparison of competing solutions to absolute measurement of variables, for example lead time. Thus, from this solution is 20% better, the solution has best output and are 95% confident it lies between 315.1 hour to 362.7 per hour. Common proportions of project phases. Problem definition 20%, model building 35%, experiments 35%, and project completion 15%. Source is Robinson. Types of simulation environment. The method used to control the flow of time can be used to classify the two major types of simulation environment. Continuous simulation. Continuous simulation is based on a user-set time slicing increment commonly called delta t. Continuous simulation is a digital approximation of an analog computer. Under the time slicing regime, each single delta t, the system was having to poll every source of logic likely to initiate an event all over the model. The system clock will progress smoothly through time. Commercial systems include iThink and Vensim. As you can see from the diagram, the delta t here has been set at 0.125 and the unit of time is hours. And the integration method is runge-kutted 2. iThink and Vensim are the two major commercial producers in this market. Continuous systems. Continuous systems have developed from the original industrial dynamics work of J.W. Forrester. Continuous systems find wide application in the softer end of system dynamics modelling. Such areas include some form of business process reengineering, BPR, and limits to growth Club of Rome type environmental modelling. System dynamics modelling can capture complex, sometimes stochastic random time related behaviour. It can model mechanical, simple harmonic motion damp spring systems. System dynamics makes much use of modelling structures involving positive and negative feedback loops. So here we have a little system with purchases, ordering delay inventory, and effects between sales and sales forecast and forecast delay. And then we'll have an output map. In the small green box, we have examples of papers being written using continuous systems to model simulation dynamics. And in this particular journal, International Journal of Operations and Production Management Volume 18, there are several similar papers. So here we have a diagram showing the list of capabilities normally required in the discrete event system, as was shown in the show flow systems video you've just seen. Some means to generate a schedule with a launch time, a part number and a batch size. A clock to measure time and to jump from event to event, as you've seen in the show flow video. Some means to model labour. Some means to develop random distribution sampling for the various sources of of randomness in the model. Decision logic, queue modeling, process modeling, process routing as in the show flow video you've just seen, graphing facilities, output data files, and reading and updating attributes as the entities go through the model. Continuous systems are not capable of supporting entities. Discrete event systems can support entities. Now, the inputs and the outputs could be read from or written to a spreadsheet or database. Entities and attributes. An entity is a data structure which moves through a simulation model. Entities must be created and then launched into a model. They should be disposed of, killed, when we no longer need them. Using an attribute, entities can be put into classes such as product types that then use that attribute is used in deciding which path the entity follows as it passes through the model. This was done in the show flow model. Memory and processing power permitting, a simulation can have any number of entities concurrently in a model. Entities can be batched, unbatched, or cloned as they move through a model. They can have their attributes read and written to as they proceed through a model. An attribute is a piece of information associated with an entity in a simulation. Each entity can have its own unique value for an attribute. Each attribute has a user-defined label that can be used to reference it. Helps to read or update attributes' value. An example could be an entity representing a batch of bats carrying two attributes. Bats, the batch size, and due-date, the batch due date. Others could be T-in and T-out, where T-in minus T-out minus T-in is the time in the system. The next piece shows a small video of the bin selection action in the Teleflex model. And here you'll see a simulated graphic of entities being sorted using the bin number attribute. Here we have a screenshot from the object-oriented simulation system called Extend. Here we have attributes for time of launch, time in, product time, prod T, batch size, bats, and time of exit, T out, tout. Here we have the diagram with the arrival time of the entity, its time in, its batch size, its product type, and its time out. Now, entities may be batched together, separate entities joined into one, and there's always an option whether you want to average the attributes or keep them retained. If they're retained, it requires a higher amount of memory. Unbatched, opposite of batched, data may have been lost. That's when a batch size is broken into individual entities. So if the batch size is 19 and the product type is 5, when it's unbatched it will break into 19 different entities. If they're batched retaining attributes, each entity will have its original attributes. If it didn't retain attributes, then the attributes on the entities will be averages of what was in the batch. Cloned, identically cloned end times using the value of bats. Matched, bats within a kick matched together. And that's the use of attributes and entities. So here we have a Teleflex passive sorting machine. This is just a schematic diagram. The actual specification was a lot more complex than this. to the Teleflex parcel sorting machine. The real specification was a 676 metre moving V-shaped groove with a maximum belt speed of 115 metres per minute. There were 280 destination parcel chutes, 8 banks of 35 chutes. These were fed by 2 banks of 4 injectors with a 60 metres per minute loading speed, and each injector outputs, according to the specification, 2,266 parcels per hour. Modelling problems. James Bond AGV composite conveyor and logic bin addressing. When modelling a bin, the belt speed over the width of the bin had to be modelled as a time delay using a conveyor. Also, as part of the bin functionality, if the attribute bin was equal to the bin address of that object, the parcel would then leave the system and be counted as being sorted. The size of the model was run at a quarter scale, 2 injectors, 70 chutes. Then we come to the choice of time unit, loading logic and 640-second run length. In this case, entities are not killed but recirculated, and the question was how to measure warm-up. Warm-up is when in a system, when it starts, it's empty, and the queues in front of the different workstations in the system will be small and parts will go through the system quickly. Such data has to be discarded. Only when the system is warmed up should data be collected. The question here was how to measure warm-up, and as we'll see, the means to measure warm-up was to recirculate the parcels and measure the queue of parcels before being re-injected. That would then show when the system was warmed up. 12 experiments were done of structured sensitivity analysis. 110%, 100%, 90% and 80% of injector output of 2,266 parcels an hour, and 100%, 80% of 60% and 60% of main belt speed, where the main belt speed was a maximum of 115 metres per minute. And yet the results of this was that the structured sensitivity analysis said that this machine, if built, would produce between 12,000 and 18,000 sorted parcels per hour. So here we have a graph which is an output of injector sensitivity test. The injector logic, which is showing shortly, was done for 110% of output, 100% of output, 90% of output and 80% of output. The operation of injector is this. The injector starts off empty. At its lower speed it loads on one parcel, then a second parcel. It then checks that the belt is free in front of it. It then ramps up to belt speed and injects the 2 parcels onto the belt. The next piece shows a short video showing the warm-up and the output of this Teleflex model. Here we have an output from the Teleflex model. The blue line shows throughput and the red line shows the queues of the parcels which have been recirculated before being injected. This being taken in this case as the measure of warm-up. Now each time before being fed to the injector, parcels are randomly assigned a bin attribute value from the uniform distribution set to sample from a range of 0 to 69 to cover the 70 bins modelled. This was done to stop any bias caused by parcels nearer to the injector being biased. It's quite technical. And below that is shown the logic for the calculation that the parcels output was 18,000 parcels per hour. Extend and object orientation. So here we'll have a manufacturing library from Extend showing machine attributes matching, etc, etc, etc. Models are built from icons or objects. These icons represent what they are. Objects come as supplied and in third-party libraries. Users can write new objects in two ways. Users can create new libraries of objects. The objects in the system can be built into meta-objects. The user can also go within the internals of the objects and write code for new objects and put these new objects in libraries. Because they can do that, third-party vendors supply the libraries for particular applications. The users can create new libraries of their meta objects. It's a mixed, continuous and discrete simulation system. It's very flexible, i.e. it's general purpose. Extend was the first of a new wave of simulation systems. Taylor Enterprise Dynamics includes what was Taylor 2, now known as show flow functionality, transplanted under a flexible object-oriented program environment. So that's Extend. And that's my explanation of object orientation. So here we have a screenshot of the Teleflux parcel model. We have one blown up piece which shows the system used to launch the parcels. It shows the input randomized, returns in stock inject 1, inject 2 to the two injectors. It shows the conveyor used as the time delay for the moving belt, not including a chute. It shows the variables for speed, whereby the speed increment is transmitted to all the conveyors in the model to run at the main belt speed. The second screenshot shows a block which shows a bank of parcels. Now we've seen in a following screen will show that in the internals of that bank of parcels. As the parcels are sorted, they are passed into an output which then graphs the throughput of the machine. So here we'll have an overview of the Teleflux model with this injector sensitivity test, the model, the schematic of the system, the output and warm-up, and then new to this diagram, attribute name bin, if input A equals B and B value equals 17, then the parcel will leave the belt and be sorted. Above that we'll see items in speed bin, speed bin, speed bin, and each one of those is a bin, and within a bin there's a conveyor aspect which is the main belt time to cross the width of the bin, get attribute which is read the value of the bin attribute, compare that with the value in the dialog box, and if they are the same, then sort the parcel. And here we have a diagram showing the injector internal logic. So within Extend, it's possible to build logic because the injector modeling has to replicate the injector. It has to do the specified injector performance in terms of parcels sorted, in terms of parcels injected rather, and it has to load one parcel, a second parcel, then ramp up to main belt speed, and having checked the belt, inject the parcels onto the belt. This is the correct operation of the injector. And the fiddle factor was operated, you'll see a slider there at 0.956. That was used to tune the system to get the original specification injector output. used in 1, used in 2, that collects, and that then produces the signal to ramp up the main belt speed. Then below you'll see the web address for extend. If you go to the web address for extend, you get lots of ideas, lots of PDFs, and a better idea of what extend does. I mentioned already there are two ways in which you can add new objects to the system. You can take the existing objects and put them together as meta objects, as has been done in the Teraflex model, each bin width being a collection of objects which are then put together to be a bank of bins. The second way you can create new objects is to write your own. So here we have the exploded view of the internal code of a plotter using something called the internal language for extend is called model. So you can take existing objects that come in the system and add functionality to them, or you can start and write completely new objects, and having developed them and checked them, you can put them into libraries. This is how third-party producers produce libraries of objects for extend for particular applications. Terminating and non-terminating systems. An example terminating system would be a bank which has random customer arrivals through the working day, then gradually empties at the end of the business day. The system empties or terminates. In this case, warm-up is not relevant. A non-terminating system would be a machine shop where, irrespective of the shift pattern being worked, work sits in queues before the work centres and the system does not empty at the end of the working day. When modelling non-terminating systems, the system queues start empty and early values of lead time do not reflect the lead times of the system being modelled. Thus, a warm-up time must be established and entry lead time and workstation utilisation data only being collected after the system has warmed up. The data prior to warm-up is normally discarded. Sub-runs and separate runs. When dealing with a terminating system, separate runs are normal since warm-up is not relevant. However, when dealing with a non-terminating system, separate runs will require a warm-up period for every run. Sub-runs require only one warm-up, but there's a danger of correlation between the data values if each sub-run is not long enough to give the necessary statistical independence. Systems like ShowFlow show the statistical correlation of the values, and if the correlation is too high, the sub-run must be made longer. Warm-up. To reiterate, steady state. When the parameter stops rising and repeatedly fluctuates within an observed range of limits, that's warming level and thus non-explosive. Explosive warm-up. When the arrival rate work content is in total greater than the capacity of the serving resource, the queue length before that resource rises forever. Cyclical warm-up. Repeating pattern, for example machine breakdown or machine clean down of a key resource. This results in cyclical warming and cooling down of this key resource. Now a fag packet sum, a simple calculation, may expose an explosive situation. Where very infrequent breakdowns can occur, these are normally ignored for modelling purposes. When an infrequent model breakdown or shutdown exists, a cyclical warm-up is likely, and the required warm-up length should be investigated. The run length should initially include several such events. There are no absolute rules, it takes practice and experience. Unlike in Teraflex, being random, warm-up requires several runs or replications. As will be seen later, because of randomness in discrete and continuous simulation, you have to do more than one run, because each time you do a run, because of the sources of randomness in the system, you'll get a different answer, and you will then be looking for the average of the different answers. So here we have an extend model with randomness in it. Over a run length of 250, it appears that the values being measured are levelling off. But if the run length is increased to 2500, with the average queue lengths over 4 different simulation runs, it's obvious this is now an explosive situation. So you must do a long run at the start of a non-terminating system to see if the system is explosive. So, to summarise, a single run length in an experiment. Terminating systems are easy in this regard. Separate runs with no warm-up and no correlation problems. Non-terminating, some very relevant factors. Subruns, single warm-up with possible correlation problems, or separate runs, each with a warm-up but no correlation problems. With non-terminating systems, an initial long warm-up long model run is advisable. This should reveal any cyclical warm-up conditions. It can only be judged on an individual basis. Here are some example suppliers of simulation systems. Delmi, a market range of applications which are strong in the simulation of automated systems, but also closely model human cycle times and body angles. Dassault System own the Delmia brand, and there is the web address for Delmia. ProModel Corporation market a range of applications. ProModel is strong in general simulation, including manufacturing. Service Model and the closely related Med Model are particularly suited to the visualization of service type situations, service businesses. So here we have a bank, a coffee shop, a global map system, and a call center. And there's the ProModel web address. Here we have Simprocess. Simprocess by Kaki is an OOPS system, that's object-oriented system, with strong process flow modelling and costing abilities. As it happens, in 1998 IBM used it as a supply chain simulator which integrates with databases. There's the web address. As you can see, orders come in split, and it allows you to display ABC reports. The system inherently and built-in models activity-based costing. And here are some of the costs built into Simprocess. Flat fee charge per entity, price per amount of resource, for example consumed, per used, hourly cost per unit, so that's the variable costs. The fixed costs has a slightly confusing interface. Actually means a calculated machine depreciation or wages cost over the respective time period. Simprocess allows you to specify that fixed costs be fully absorbed for the cost period, absorption costing, or that the idle time cost be kept out of the reported costs. As you see from the advert, Simprocess is data analysis, process mapping, activity-based costing, given event-driven simulation, and having built the model, the design of experiments. Here we have www.simulationdynamics.com. This company has taken Extend, then built their own libraries of functionality using Extend. So you build equipment from flow blocks, you build operations from equipment, you build systems from operations, and you build plants from systems. So starting with small parts, you can then model the automation and processes and queuing and breakdowns of a whole factory. And that's the web address there. So here we have a simulation to demonstrate why we need more than one simulation run. In this model, extend model, very simple but very powerful. Orders arrive according to a triangular distribution, and the batch size which arrives is drawn from a uniform distribution. So order sizes can be either 2, 3 or 4 items. As they come in, the parts are written to do with a value of 0.8. That's the processing time on the process. The process breaks down according to a Weibull distribution, and the time of a breakdown, once it's broken down, is according to a triangular distribution. And as we'll see in the video, the number of breakdowns affects, and the number of breakdowns is random, affects the total production for that simulation. The system will give you a different output each run, so you have to have more than one run. So here we have an output from the simulation. Buffer length in blue, which obviously increases when you have a breakdown. Y2 is breakdowns, green is batches, and pink is output. So you have output, then you have a breakdown, output stops, you have another breakdown, output starts, and depending on each run you get a different output and a different number of breakdowns. This means that in a simulation where you have randomness, you have to have more than one run. The need to emulate and replicate randomness. Aspects of this are: a particular distribution is randomly and uniformly sampled across the user's set range of values. The simulation system must contain algorithms to convert a random number stream into a stream of random samples of the standard distribution being emulated or modelled, for example log normal or Poisson. Two comparable experiments should use the same set of random number streams. Hence a need for repeatability and random streams exists using user set random seeds. Each experiment will normally consist of several runs. The pseudo-random generator involved should not repeat itself within a very large number. The generator should not produce its seed number and thus repeat the sequence in less than 2 billion numbers. This is known as the cycle length or period of the random generator. These numbers lying in the range 0 to 1 are then fed into the appropriate standard distribution algorithm such as normal or Erlang. So do they work? So here we have a diagram and chopped off distribution for normal. A normal distribution set at mean 60, standard deviation 20, and run for 1,000,000 numbers in a 1,000 column wide histogram. The larger diagram shows the shape of the normal distribution curve in this 1,000 wide histogram. If you look closely at the outputs for seed 1 and seed 2, looking like a collection of skyscrapers, the values between the two outputs are slightly different. So each time you have an output and a different seed number, you get a slightly different output from the standard distribution generator, preventing inaccuracy when using random numbers. Internally, the majority of simulation systems only have one generator. They then subdivide this into 10 or 100 separate streams. They also use the user to set his own seeds. The system will then automatically have the different sources of randomness on different seeds, each offset by say 10,000 or 100,000. As a rule, sources of randomness within a model run should be on different seeds, and thus on different independent sections of this 2 billion long circular stream of numbers, hence avoiding a source of correlation since confidence intervals assume statistical independence. So finally, here we have a comparison between continuous simulation and discrete event simulation. Continuous simulation operating on delta T can be used to model the UK economy, soft systems and behavioural problems, continuous control problems and models of continuous processes. It could be one product system design, Blu-ray design with combined continuous and discrete elements, i.e. extend, and models of logistics chains and industrial dynamics. Discrete and continuous can do both of these. That's the overlap. Now, continuous systems can have their flow discretized into gobbets, so that each gobbet could represent, for example, a single product. But the simulation producing that product can only have one product type, because the gobbet is only a mass of fluid going through the pipes of the continuous system and cannot carry attributes. Discrete event systems have entities and carry attributes, and they can be used for information flows in business system design and business process re-engineering, information network packet flows, call center operations, hospital operations, order scheduling rules, and as I've tried to describe earlier, capital investment appraisal and budgeting. Because discrete event systems can model cost, you can have a far superior way of comparing competing budgeting investments as you go. You can compare potential projects far more carefully. You can vary the assumptions used in the project and compare projects. In discrete event systems, there's one single global time clock, and that time clock jumps from event to event, as we've seen in the video. Finally, in this little short course on simulation, due to the limitation in time, discrete continuous simulation has only been lightly covered. In real world, discrete next event simulation with entities and attributes is more important. Finally, to impress and educate you, there's an extend continuous simulation of chaos theory, in particular strange attractors in chaos theory. Here endeth this video.